Welcome to Mission Control Houston. I'm here with Dr. Peter Voorhees, the principal investigator of one of the experiments on the International Space Station. This is a rather special run for this experiment because it's one where we brought the samples up on the SpaceX Dragon vehicle and we'll be returning them home when the SpaceX Dragon comes back on May the 25th. So it's a very quick run, and Dr. Voorhees will tell us a little bit more about his experiment and why it's important for it to come back so quickly. Welcome to Mission Control.
Thank you. It's a pleasure to be here.
Now, you are here for some regular space station program science meetings about
right.
how we coordinate all the research on the station, right?
That's exactly right. That meeting starts in a little bit.
All right. Well, we appreciate you taking time to join us today. Tell us a little bit about your experiment. What do you call it?
What we're interested is in studying how these structures called dendrites evolve. And dendrites everyone has experienced. So if you go out in the, you look at your windshield in the winter, and you'll see frost on the windshield. Those little things are dendrites. Ice crystals are dendrites. Snow. And what happens when you make materials is they're solidified from a liquid, and when they solidify, they form dendrites. And the properties of the material are inherently linked to the way what these dendrites look like. And what we're studying in space is how they evolve so that we can understand better how to control these dendritic structures on the ground and improve the properties of materials.
Okay. And how long have you been working on this kind of research?
Oh, my first experiment for NASA was proposed in 1985.
And so you did some space shuttle experiments too, right?
Did some space shuttle experiments as well. So I've transitioned from the shuttle now into the space station era.
Okay, great. And tell us the name of this particular experiment.
This is called coarsening in solid liquid mixtures.
Okay. And what are the advantages of learning how these dendrites work and solidify in microgravity?
Yeah, microgravity is really essential because what happens is when we do the experiments on the ground, it's just like ice cubes in a drink. The ice cubes settle to the top. And so when we do the experiments on the ground, the dendrites settle to the top. And that's exactly not what we want. We want them to be uniformly distributed in the liquid. And so in space, there's the absence of gravity, and they stay approximately fixed in space, and we can watch these things evolve during the experiment without having them settle.
Okay. Now, what material are you working with?
The material we're using is lead tin. This is commonly called solder. But the nice thing about lead tin is that it melts at a very low temperature. It's only 185 degrees centigrade, so it's easy to do the experiments in space.
Okay, great.
The furnace only takes 11 watts of power.
All right. And so, again, you've got a number of these experiments and samples that have been worked on the space station already.
That's right.
This is a little bit different because it went up and it's coming back very quickly. Why is that important?
This is one of the, I think, the real highlights of this particular mission, in the sense that we can send the experiments up, have them done, and return quickly. Because what happens is that the samples degrade once they're solidified, after they're solidified. And it makes the analysis of the samples that much more difficult if we have to wait a long period of time before they come back. So the ability to retrieve the samples very, very quickly is really a really real plus for us.
Okay, and so these samples are going to come back on March the 25th. When do you expect to have them in your hands?
March the 28th.
Wow, that's a pretty quick return.
Yes.
After a splash down the Pacific Ocean and then a road trip back to Texas.
They go to Long Beach, and they take them out of the furnaces at Long Beach and put them into dry ice and send them to Northwestern.
Great. And what kind of analysis do you do on these?
Yeah, what we do when we get them back in the laboratory is that my students and postdocs will be working on cutting them up and looking at the insides of the samples to look at the dendrite structures.
And tell us a little bit more about the potential benefits to people here on Earth from what we learn about this.
Yeah, it turns out that the properties of materials, let's say aluminum alloys that are used in bicycles or used in engine blocks, are inherently linked to what these dendrite structures look like. In other words, what these Christmas tree-like structures look like. And if you can understand how to control them, then you would understand how to improve their strength, improve their ability to withstand vibrations over long periods of time. And so what we'll do is we'll take this information that we get from these experiments and use that in codes that will predict the properties of materials.
So I'm guessing this would apply to just about anything that's an alloy, a mixture of metals.
Absolutely. That's right. That's right. There are about a billion trillion dendrites produced every day in the casting of steels and aluminum alloys that are used in virtually every material that every application you can think of. And so it's inherently linked to a lot of the properties of these materials.
And of course, launching things to space is pretty expensive, and so we're not talking about making a factory to do these in
No, no,
microgravity.
no, no.
But can you translate what you learn into improved processes for manufacturing on the ground?
That's precisely the whole idea. We're not manufacturing in space, but we're using the information to improve what we know about the processes and hence impact things that we do on the ground here on Earth.
Okay. Tell us a little bit about you. Did you always know you were going to be doing research in space?
No, I didn't know when I did my PhD. Of course, I never thought I'd ever have the opportunity to do experiments in space. It's just that the microgravity environment provided by the ISS or the shuttle is such a unique platform to do these experiments, and you can really focus on the important issues associated with material science in many cases by doing experiments in space.
So we know you're at Northwestern in the Chicago area now.
That's right.
Where are you from originally?
I grew up in Staten Island, New York. It's a borough of New York City, and spent some time at NIST, National Institute of Standards and Technology in Gaithersburg, and then moved to Northwestern now almost 20 years, 25 years ago. So I've been there ever since.
Are you missing the cold weather yet?
Oh, I couldn't believe how warm it was when I arrived yesterday. It's like 88 degrees.
All right. Well, Dr. Peter Voorhees, thank you so much for joining us here in Mission Control today. Explain a little bit about your experiment. Good luck in your meetings here and on your travels back home. And we look forward to hearing the results of how this unique opportunity to get your experiment up and down quickly works out.
Fantastic. It's been a pleasure to be here.
Thank you.
Thank you.